just to revise, we've been looking at this idea of exponential growth and decay, right? One of the things we haven't really done, or I haven't at least, you guys I think have looked at some questions that have asked you to do this, is we have not plotted these, okay? Now I just want to remind you about this before we move on to decay, because I didn't address decay situations at all yesterday. I'll do a couple of examples this morning. What does this look like? Well, because it's an exponential, and I've just put both of the common forms here because it doesn't matter whether it's capital A or P naught, they both refer to your initial condition, right? What does the graph look like? Well, we're super familiar with what exponentials look like, right? So this is the kind of shape, this is the kind of behavior that we're getting, okay? There's a few features that are missing from here. What else could I add to make this sketch a little more accurate? I could add an intercept, right? What is the intercept? It's either A or P naught, whichever you define it to be, okay? So let's call it A for now since it's my first one. Is there anything else I'd like to add on there? I suppose it would be nice to have a point for scale. It's a bit arbitrary at the moment because it's all sort of constants that we have no idea what they are, okay? But there is one other feature. If I just asked you, nothing to do with exponential growth and decay, just to draw this thing, just to graph it, okay? There's one glaring feature that's missing. Can anyone tell me what it is? It's the asymptote, isn't it? So it should be here across the t-axis, okay? Now, while we're talking about the t-axis, it's probably important to mention that you'll notice I have the left-hand side and the right-hand side of the t-axis. I have negative values for t and positive values for t, okay? Now, we're used to thinking about sort of measurements being positive only, right? Can anyone tell me why it actually is kind of worthwhile to have both sides of the t-axis? Any suggestions? Excuse me. Let me pose this question. The origin, right? T equals 0. Have a think about some of the questions that you've had a look at already. What does t equals 0 signify, usually? Or can anyone think of any examples? It's your initial value, right? Now, often they will say, you know, in year 1995 or something like that. And they say, we call this the initial value, and they give you a population, okay? But of course, we know, that's why we call it 1995, that time doesn't just start, the universe didn't just start existing in 1995. There was time before that, okay? The questions you've been looking at, they mostly have just been thinking about progression. But if this model works, if it's consistent, right, if the situation they've given to us matches this exponential growth curve, then we should be able to just as easily go back in time, right? You could say, well, 1975, in this scheme would be a t-value of negative 20, right? Negative 20. Something like that, which is totally sensible. It's a sensible value. It makes sense, okay? So don't just, if you've been drawing your graphs and you've been writing off the negative side of the t-axis, add that back in now, or for subsequent graphs you've got plenty more to draw, okay? Now, being that this is an exponential growth situation, what does an exponential decay situation look like? What's the difference in terms of the equations? There's a negative. Where's the negative? It's up in the index, isn't it? So it'd be something like this. Okay. Now we're used to seeing, e to the x and e to the minus x, right? E to the negative x. Having that negative sign there, it flips things around horizontally, doesn't it? Okay. So this is the shape we're getting. Okay. Now, just like before, this is why I was drawing attention to the asymptote. Okay. Just like we have an asymptote here, the asymptote is exactly the same. Okay, oh, sorry, I'm a bit off the axis there. So that's p equals 0. Now this is important because let's see if we can describe what's going on here in terms of our exponential growth and decay language, right? We know why, algebraically, why this never gets to 0, right? Because no matter what large values of t you stick in there, right? For example, if I put in 100, okay, you're going to get a e to the negative 100k, which is a on e to the 100k, right? Which, depending on your value of k, is probably a really small number, right? But it's not 0. And if I went further, if I went like time a million, something like that, that's right, you're still going to get a very, very, very small number. Did I put too many zeros? No, it's okay, right? But you'll never get to 0 algebraically because there's no value you can stick in the denominator, right, that will make the whole thing equal to 0. Okay, now that's fine algebraically, but can you explain to me, in terms of the language of exponential growth and decay, why is it that he never gets to 0? Why can the population or the quantity or the mass or whatever it is, why can't it ever get to 0? Because it's impossible? Why is it impossible? Do you wanna hazard a guess?
It's defined in terms of itself, like it's defined proportionally in terms of itself.
Okay, let's go after this. What is the differential equation? You remember I introduced that idea. Really, it's a first order differential equation. I wonder if you can guess what a second order differential equation would look like. We're thinking about this for now. We're thinking decay. So that's why there's a minus sign out the front, because when I differentiate this, the negative will hop out the front, just like the k does. All right? Now, there's this proportionality idea. Yesterday I said, if you understand this, everything about exponential growth and decay will make sense. Okay? The rest of it is just number crunching. Okay? I think I know what this means. Okay? As you get further along in terms of time, right? 1,000 years, 1,000,000 years, all those kinds of things, right? What can you tell me about the population, or the mass, or the quantity? What does it look like? Well, the actual population itself is very small, isn't it? Very, very, very small. Okay. Now, if the population is small, what that implies is that the rate that the population is changing, or the rate that the mass is changing, or whatever quantity it is, it's also getting smaller, right? It's getting smaller at the same rate. That's what proportional means, okay? So the closer and closer you get to 0, the more you're slowing down, right? Does that make sense? The less stuff there is, the less the rate of change will be. And that's why you never get to 0, okay? So, I want you to be able to understand and interpret and explain what's going on here, not just in terms of this language, but the fact that, what did these stand for? They stand for quantities and populations and people and so on.